Hello, I'm Juan, and together with Richard, we did the unsupervised and meta learner application studies. For my setup, I use the set role to have the class as the target attribute, and we set that target attribute to the label. We then normalize that data and send it to the cross-validation module. Now, inside the cross-validation module in the training section, this is where we will have all our ensemble learners. And on the right side in the testing, you'll see that we have the apply module and the performance, which gives us our matrix table. Before we start, we have to normalize our data. And the way we do that is we go inside the normalize module, change our method from Z transformation to range transformation, and leave the min and max to their default values. So here we're using the bagging ensemble. And if you look at the matrix table, you'll see that the 11th row has a clear bias towards it. Now, we're not sure why this is happening, but if we were able to clean up our data a little more and look into the specific rows, I'm pretty sure we can figure out why. So here we are also using the backend ensemble, but this time with our DARPA set B. You'll see that we have a 99.94% accuracy, and you'll see that we still get some inconsistencies with the predictions, but it's way better than the first data set. So here we have the second ensemble learner, the Bayesian boosting, and you'll see that we have a higher accuracy from the bagging ensemble. But similar to the last ensemble, on the 11th row, you see that there's still somewhat of a bias, but not as much. And with our Bayesian boosting on our dataset B, we get 100% accuracy. Now, there are still some mispredictions, but that's normal in this case. So here we're using the AdaBoost ensemble learner. And similar to the bagging ensemble learner, you'll see that the 11th row kind of still has a bias towards it, but not as much. And we do have a slight increase in our accuracy for this table. So still using the AdaBoost ensemble learner with the DARPA B dataset, we still have 100% accuracy, but we have more predictions that are incorrect. So using the random forest ensemble learner, we get a somewhat similar accuracy, the AdaBoost, and we still get on the 11th row a very biased prediction. This time with the DARPA B dataset, we get 100% accuracy. You'll see that our columns and rows are mostly 100% except one. I will now pass this off to Richard.
Hey guys, this is Richard LaBelle. I carried out the unsupervised application study for our group. Unsupervised clustering is the challenge of labeling and grouping data in the dataset based on the outcome of the different algorithms attempted in the final project. For each of the algorithms tested, we use basic Z transformation normalization to normalize the data between 0 and 1. We also decided to trim off any non-numeric attributes by using select attributes in RapidMiner. For resampling the data, we decided to trim the data down a lot using absolute bootstrapping sampling. We kept the sample size at 1000 to reduce runtimes for the dbScan and expectation maximization algorithms. K-means ran at a much more reasonable time, so we left the sample type as relative with 100% of the data. Now to actually look at the RapidMiner processes used to test the different algorithms. For each process shown, they only contain dataset DARPA A, although I had recorded results for both datasets A and B. Once we resampled the data, we passed the data to the k-means algorithm shown here. Shown here are the parameters that differ from the other processes. As I mentioned earlier, k-means was sampled using relative ratio to the data. To the right of that are the parameters for the actual k-means algorithm. I mainly wanted to note that I had to use Bregman divergences in order to get any of the performance testing blocks to work successfully. Next we have the k-means algorithm results, shown here for the DARPA A dataset. The algorithm clusters do not include a lot of data aside from cluster 0. I believe this is because the algorithm had difficulty identifying similarities in the data to cluster based on. Looking at the much smaller DARPA B dataset, we did not find much improvement in clustering efficiency. The performance vector here also contained very large values. Now we have the dbScan algorithm. For this process and for the next, I was unable to get performance testing to work aside from the cluster density performance testing block, which required the extra blocks in the process, like data to similarity block to actually see how the algorithm performed. For this process, we needed to update the dbScan algorithm to use numerical measure for the measure type, which forces us to use Euclidean distance. The results for the DARPA A dataset, we see majority of the clusters have an average distance less than 5 within the cluster, aside from the few that have much larger distances. Although not perfect, this is better result than what we have seen with the k-means algorithm. Using the smaller dataset, DARPA-B, the average distance across all datasets had decreased, although all but one cluster had an average distance lower than 5 with the one cluster. Finally, we have the EM algorithm, or the expectation maximization algorithm. Once again, the only form of performance testing I was able to get working with this resulting clustered data was the cluster density performance block in RapidMiner, shown near the end on the right in this image. The parameters for the EM algorithm included the settings needed for the initial k-means run. Everything else was left as default. Now, the results for the EM algorithm on the DARPA-A dataset showed little work done as far as clustering the data together. Although it contained the same sample size of the dbScan algorithm, the EM algorithm was only able to group the data into one other cluster, leaving the average cluster distance to be very high. I believe this algorithm would have performed better had it been given the entire dataset, but in order to complete the task within a couple of days, I left the dataset sample to be very small. And to wrap up the results for the presentation, the results for DARPA-B are slightly better, but only due to the dataset being smaller in size and range.